to sum up this particular chapter, see, we started off by understanding what is a nucleus and what is there in the nucleus, correct? Protons and neutrons are there in the nucleus. After that, we discussed about couple of parameters of nucleus, like what is the nuclear size, R is equal to R naught a power 1 by 3. And we discussed about the density, which is around 10 to the power of 17 kg per meter cube, correct? And as we move on further about understanding how a nucleus is there, we understood about the nuclear force, correct? Nuclear force, the strongest force in the nature, that is the nuclear force. And it is charge independent, like proton, 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 neutron, or neutron, neutron. It's one and the same, correct? And once we are done with the nuclear force, then what we have that atomic mass unit, the mass of one nucleon, 1/12 the mass of the carbon-12 isotope. We took it that way, we understood what is 1 AMU. And if you have 1 AMU, using the Einstein's equation, E is equal to mc square, if you convert the entire mass into energy, how much is that energy? That also we discussed, correct? 1 AMU is 931 mega electron volt. This is the mass or mass energy equivalence, you can say. Once you have that energy equivalence, whenever you have reaction, there is a mass defect, and that mass defect turns out to be the energy, correct? Energy in what? Energy in binding the nucleons. This is where the binding energy is very, very important, and this is where the binding energy comes. We bind the nucleons, or basically not we, as in the nucleus is going to bind by itself, correct? How much of energy do we need to split that apart? That is the binding energy, correct? And we are most concerned part of this one is binding energy per nucleon. How much of energy do we need for one nucleon to separate it, correct? Because this gives the stability, where we come across this curve, isn't it? Binding energy per nucleon curve. And in that, we noticed lighter elements are less stable, heavier elements are less stable, but in between, they are very stable. Especially iron. Iron is the most stable element, correct? And it has the highest binding energy per nucleon, 8.8 mega electron volt per nucleon. It has the highest binding energy per nucleon. This is where we understood about the stability of the nucleus, isn't it? So when we talk about stability, it means that no nucleon should disintegrate by itself. For that, we have different parts, as in different things. How binding energy per nucleon works, how number of protons and neutrons are going to work, the ratio. And also we understood that even number and odd number of protons and neutrons, they also matter in the stability of the nucleus, correct? This is about the stability. And once you know that the nucleus is stable, well and good. If it's not, what happens? This is where radioactivity comes. Radioactivity, it's that spontaneous process where, the nucleus is going to decay or disintegrate. And as and when it disintegrates, it emits 3 types of rays: alpha, beta, gamma. Correct? When alpha occurs, the mass number reduces by 4, atomic number reduces by 2. And in the daughter nucleus is going to have some sort of energy. Beta, what happens? In beta, it's fast moving electrons, isn't it? And in this fast moving electrons, why do we have electrons? The neutron disintegrates into proton, electron and energy. Correct? So in a beta decay, the mass number remains the same, whereas the atomic number increases by 1. Correct? This is what happens in a beta decay. And in gamma decay, gamma decay occurs after alpha or beta. The reason is the nucleus will be in the excited state, and that has to come down to the normal ground state. That's why we have the beta decay. So we have alpha, beta, gamma, 3 types of decay. Correct? And since you know that there is going to be decay, now after some point of time, how many atoms are actually remaining in the system? This is where we have the formula n is equal to n naught e power minus lambda t. Now what was lambda? Lambda is the disintegration constant or decay constant. Correct? N naught, original number of radioactive particles or atoms. N is at this instant of time, how many radioactive elements are there or how radioactive atoms are there. Once you understood this one, the same type we understood what is half-life, what is mean life, what is activity, correct? Half-life, 36.7% or 36.8 you can take it. 37, take 37. 37% should be there. That whatever time we have, that gives us the disintegration constant, correct? That's not the half-life, that's the disintegration constant. Lambda. Half-life is what? The number of atoms should reduce to half. How much of time are we taking? That is the half-life. Average life, tau is equal to 1 by lambda. Correct? Higher the disintegration constant, lesser is the average life. Now comes the activity. How quickly the radioactive element is decaying. How quickly? Is it very quick or is it very slow? That's given by A is equal to A naught e power minus lambda t. Correct? Now, the general formula, A by A naught is N by N naught, half to the power of N or half to the power of T by T. So, once you have this one, now that you are very clear what is radioactivity, to be honest. Now comes the nuclear reactions. Correct? Alpha, beta. Nuclear fission, nuclear fusion. Fission, heavier ones will split into lighter ones. And in fusion, it's the other way around. Lighter ones will fuse to form a heavier one. So when we talk about fission, main element is uranium, U-235. 235 splits into krypton and barium along with 3 neutrons and a lot of energy. But in fusion, 4 hydrogen will combine to form helium, 2 positrons and a lot of energy along with neutrinos and all those things. Fission and fusion. Understand the difference between these two? Okay. And the last part was the nuclear reactor. A device where we actually use fission to produce energy. Understand the parts of nuclear reactor. What is a fuel cell? What's a moderator? What's a control rod? The coolant? The heat exchanger? Everything. So this basically is the entire summary of nucleus and radioactivity chapter in your syllabus.